Good morning. I'll solve some problem on similarity analysis. One illustrative problem I have considered from incompressible flow and one for compressible flow. So this first one is for incompressible flow. So the problem statement is a radial flow hydraulic turbine is required to be designed to produce 30 megawatt under a head of 14 meter at a speed of 95 RPM. So for the prototype turbine, the power has been stated, head also given, and its RPM. A geometrically similar model with an output of 40 kilowatt and a head of 5 meter is to be tested under dynamically similar conditions. At what speed must the model be run, and what is the required impeller diameter ratio between the model and the prototype, and what is the volume flow rate through the model if the efficiency can be assumed to be 90%. So the model power output 40 kilowatt has been stated under a head of 5 meter, and it is dynamically similar machines. So it has been asked to evaluate the model speed, the diameter ratio between the model and the prototype, and the flow rate of the model. Let's go to the solution. Now subscribe 1 I have referred for prototype and 2 refers for the model. So one can easily write from the similarity rules that P1 divided by N1 to the power cube and D1 to the power 5 is equal to P2 divided by N2 to the power cube and D2 to the power 5. So from this relation, I can express the ratio of D2 by D1 as P2 by P1 to the power 1/5 and N2 by N1 to the power 3/5. Put the values of P2. P2 is for the model, power has been given as 40 kilowatt, and P1 is 30 megawatt. So I can create a relations between D2 by D1 to N1 by N2 with some constants. Again, if we come from the head rise coefficient, that H1 by N1 D1 to the power square is equal to H2 by N2 D2 to the power square. This is non-dimensional head. For both the model and the prototype must be the same. Again, with this, I can have a relation between D2 by D1. You see, please go through this right up. That is D2 by D1 is equal to H2 by H1 to the power half N1 by N2. And thus I get a relation of d2 by d1 is equal to 5 by 14 to the power half into n1 by n2. So this relation, and the earlier that I have developed this one, if we equate, then I'll get this equation, right? Which is 0.266 into n1 by n2 to the power 3/5 equal to 5 by 13 to the power half into n1 by n2. And from here, you can evaluate n1, n2. And n1 is known to you, so you can calculate n2. You have calculated n2, I got around 721.4 RPM. That means model has to rotate by 721.4 RPM. Now, suppose now if you use either this equation or this equation, what is that? This equation. Since n1 by n2 is known to you, you can calculate diameter ratio. So that I have done in the next slides. d2 by d1 is equal to 5 by 14 to the power half into 95 by 721.4. So model scale ratio is 0.079. So this is the second answer. The third, we'll have to calculate the model flow rate. Now, efficiency eta, I can write P2 divided by hydraulic power, that is rho G Q2 into H2. So from this relation, I can express Q2, that is flow rate through the model, is equal to P2 divided by eta rho G into H2. Now everything is known here. So P2 around 40 kilowatt, H2 is 5. So if you put all the values, you will get Q2 as 0.906 meter cube per second. Thus, the model flow rate is 0.906 meter cube per second. Thus, I got the answer. Model speed at 721.4 RPM. Model scale ratio is 0.079 and model volume flow rate is 0.906 meter cube per second. The second problem was an axial flow compressor is designed to run at 4,500 RPM while the mass flow rate being 65 kg per second when the atmospheric conditions are 1.0, 1.3 kilopascal and 15 degrees Celsius. On the day when performance characteristics is obtained, the observed atmospheric temperature is 25 degrees Celsius. The pressure at the entry to the compressor is 60 kilopascal. So please note that when the characteristics is obtained, both the temperature and the entry to the compressor pressure has changed. What is the corrected speed at which the compressor must run? That will have to evaluate this. And second, also evaluate the mass flow rate obtained in the test. Let's solve. For compressible flow, we know the representation of non-dimensional speed, which is represented as N1. It's not truly non-dimensional. It's represented at n by root over T0. So I can write n1 by root over T0. 1 must be equal to n2 by root over T02, where 1 refers to the condition 1, and similarly 2 subscripts 2 refer for condition 2. Now from here I can evaluate into all other data sets unknown to you. So I have evaluated corrected speed as 4577 RPM. Similarly, we know the capacity as m root over T0 by P0. So I can write m1 root over T0 1 by P0 1 must be equal to m2 root over T0 2 by P0 2. So from here I can calculate m2, and I have evaluated m2 as 37.85 kg per second. So thus I have shown you an illustrative example for incompressible flow and one for turbomachinery handling compressible flow. Thank you for listening.